Hello everyone, my name is Karan and today I am going to explain you about one of the most important algorithms of machine learning, that is support vector machines. So we are the students of ASSM Institute of Information Technology Pune. This PPT is presented to you by a group of three: Ashish, Karan and Neeraj. Today the topics we are going to discuss is what is SVM, the algorithm steps of SVM and some of the practical examples of it. So what is SVM? So SVM is nothing but a supervised learning model that classifies the data by finding the optimal hyperplane. The key innovation of SVM is maximizing the margin between support vectors, which are the closest data points to the hyperplane. This approach enhances generalization and reduces the overfitting. SVM excels in high dimensionality spaces, and it is particularly useful in the datasets where there are more features than samples. Now understand what are margin and hyperplane. Hyperplane serves as a decision boundary in SVM, separating different classes. The margin is distance between the boundary and the nearest data point, known as support vectors. What SVM does is that it ensures that the decision boundary is as far as possible from the nearest data point, which leads to better generalization and lower VC dimension. Now let's see what are support vectors. Support vectors are the critical training points that lie on the margin borders. They are essential for defining the hyperplane and decision boundary. SVM uses only the support vectors to determine the model, making it sparse representation. This leads to computational savings and efficient memory usage. SVM is used to create interpretable boundary, especially in kernel-induced features, making it easier to understand the model. SVM uses compressed dataset as it is concerned with only support vectors, which helps in efficient model generation. Now let's see what are the various algorithm steps of SVM. The first phase is data preparation phase, where the data cleansing and scaling is done by removing the missing values, encoding categorical data, and scaling numerical features. Here the data is split into training and validation set to evaluate the model. Now here are the three main steps of SVMs. First is formulating the primal problem, where SVM tries to draw a clean line between the classes and makes it as wide as possible without misclassifying the data points. In the second step, the dual problem is derived by using Lagrange multipliers to simplify the SVM math. It changes it into the new form called the dual problem, and the dot products is replaced by the kernels, and SVM can now work on non-linear data also. The dual problem is convex, so it always gives the best solution. Next, the kernel trick for efficiency. The dual formulation enables the use of kernel trick, allowing SVM to handle non-linear data efficiently. Now comes the solving and model retrieval. The problem is solved using quadratic problems like sequential minimal optimization or Lagrange multipliers or kernel methods. Then comes model construction, where the SVM is constructed by computing the weight vector and bias terms. The data is stored into coefficients for efficient prediction of new data. Now let's see some of the practical examples of it. One of the most classical example of this is text classification, where first the text is pre-processed and then the model is trained and evaluated. The pre-process of text data happens by lowercasing, removing stop words and converting into TF-IDF vectors. Then the SVM model is trained using the pre-processed data and achieved high accuracy. Support vector represents small fraction of training data demonstrating efficiency. Now here one point worth considering is that SVM along with classification can be used for both regression and outlier detection. An extended SVM can be used using the epsilon insensitive tube, which penalizes prediction outside a tolerance margin. Also, one class SVM for outlier detection can be used by learning the support of the normal data and flagging deviations. These both examples show the versatility of the SVMs beyond classification. Now let's jump to the conclusion. The strength of SVM is that it offers accurate, memory efficient models that is useful against overfitting. It also handles high dimensionality data in a very efficient manner. But there are limitations of SVMs, like it is sensitive to hyperparameters and struggle with very large data set. Also, it could be difficult to interpret SVM in non-linear cases. The third is the scalability challenges. While SVM works well with moderated size dataset, it becomes challenging when it comes to the large dataset as it's become computationally complex. The fourth is interpretability issues, where interpreting a nonlinear SVM model could be difficult and hence limits its applicability in some of the domains. Hence, the future scope of SVM could be that we could improve these limitations and improve its efficiency using AI and deep learning. Hence, increase the interpretability of SVM. So that's all about SVM, and thank you so much for watching this video. Thank you.